Hey everyone, I am back with more gases for you in AP Chem, page 10 of 16 of your outline, and we're going to be doing some tricks with the ideal gas law today. We're talking about gas density and molar mass. So we'll start out with just some basic algebra stuff. PV equals nRT. And we have to acknowledge that PV equals moles. Moles is actually mass divided by molecular weight times RT. And we can rearrange that for molecular weight to equal MRT divided by PV. Okay? Now, that's a very convenient formula in laboratory situations. It works really well for us. Also notice it's got mass over volume, so we could also say that molecular weight equals dRT over P. Okay? And it is possible to rearrange this for density, which is pressure times molecular weight over RT. These are two very convenient equations for homework problems, but this is the really good one right there. That's the one we use in a laboratory situation because we don't really have devices that measure density directly, but we can measure mass and we can measure volume. So let's imagine that we have a rigid container that's holding a gas, and I'll make it just 6 random circles in here to indicate particles, okay? And they're flying around and bouncing off the walls. Let's say this container has a mass of V. Now, what happens if suddenly we make them, it has a volume of V. I think I said mass there. It has a volume of V. So, what if I make the volume 1/2 of what it was, but I don't change the number of particles that are in there? I now have the same number of particles over a much smaller volume, which is indicating that it is going to be denser or more tightly packed. More molecules per unit volume. More molecules per unit volume. Okay. They're going to be closer together here. Now, of course, we are assuming when we do something like this, we are not changing the temperature or, other factors like that. Okay? All right, so mathematically, we've actually seen some questions like this before in Honors Chem, but we'll run through a few of them just so you can get an idea. What is the density? Uranium hexafluoride, UF6 at STP. Density equals pressure times molecular weight over RT. Now the pressure is 1.00 atm. Molar mass. Okay, so I got a uranium at 238. I've got 6 fluorines times 19. That comes out about 352. Okay, so 352 grams per mole. R 0.0821 liter atmosphere per mole Kelvin, and standard temperature is 273 Kelvin. Atmospheres are gone, moles are gone, and Kelvin cancels also. I'm left with grams per liter. That's good. That's actually an appropriate unit for density, and I get about 15.7 grams per liter. Now, this is a gas. It's not terribly dense. Remember, the density of water, liquid water at room temperature, is about 1 gram per milliliter. Okay, so this is substantially less dense than liquid water. Okay, now, interesting scenario here. Same thing, but at a higher temperature and a lower pressure. Physically, what does that mean? Higher temperature, the particles are going to be moving faster, which is going to tend to cause them to spread out more, be more distributed. Lower pressure means that we do not have as much force pushing in on them, and again, they're going to tend to spread out more. So density equals pressure times molecular weight over RT. My pressure is 0.5 atmospheres. Same gas, so 352 grams per mole. Excuse me, 0.0821 liter atmosphere per mole K, and 500 Kelvin, much higher temperature. Okay, atmospheres, moles, Kelvin. Now I've got grams per liter again, and this time it's 4.29. Much less dense at these conditions than at our original set. Okay, again, higher temperature is going to cause the particles to spread out more. Lower pressure will allow them to spread out more. That's less dense. Okay, now, just one more basic style question. The density of carbon tetrachloride. Okay, I wanted to go with a smaller molecule. Pressure times molecular weight over RT. Now, okay, 714 torr. 714 torr. Carbon tet. Okay, I added it up and I got 153.81 grams per mole. I'm going to have to use a different value of R this time. I'll use 62.4 liter torr per mole K. 125, so add that to 273, 398. 398 K. Same thing, units canceling, the torr is gone, moles and Kelvin. Okay, you have a 4.42 grams per liter. Okay, so what I'm seeing pretty consistently here is that the density of gases is relatively low. Now, let's start using this idea. Okay, it's not often that you're actually going to be asked to calculate the density of a gas. Okay, but you are going to be asked to identify molecular weights, and this is one of the labs that we do this year. So molecular weight equals dRT over P, dirt over P. That's what the cat does in the litter box, puts dirt over its P. 2.67 grams per liter. Okay, R 0.0821 liter atmosphere per mole K. The temperature, 25 degrees Celsius, is 298 Kelvin. Okay, and the pressure is 1.00 atmospheres. All right, so when I do this, I'm seeing Kelvin canceling. I'm seeing atmosphere canceling. Okay, so liter will be my next one to go, and I'm left with grams per mole. And since I'm looking for a molar mass, that's good. 65.3, give or take. So if I'm trying to determine between the gas SO2 and SO3, I can add up their molar masses. Okay, and it turns out that SO2 is just about 64. Okay, 16 times 2 for the oxygen is 32. 32 for the sulfur, so that's about 64. This is pretty close. Add up that one, and I'm way above 64. Okay, I'm up about 80. So this gas would be SO2. Okay, there we go. All right, that's good. That's page 10 of this outline.